Assalamu alaikum, students. Can you hear me?
Alaikum salam, yes.
Okay, inshallah, today, last week we completed chapter number 17. Inshallah, today we are going to start chapter number 18. And this is going to be a short chapter in the sense we are going to start today, and inshallah, we are going to end today as well. So, by finishing chapter number 18, we are actually done with our syllabus. So, So today practically will be the last class for dynamics. After that, in case if anybody wants revision, then we can I can come during the class time and we can revise some of the material. We can discuss some of the problems. But anyways, the attendance will not be compulsory, and so it's up to you if you want to come or not. So today will be the last class in the regular class sessions for dynamics. And inshallah today we are going to finish uh, the complete material for the course of dynamics. So chapter number 18, chapter number 18 is about uh, kinetics of rigid bodies, but using the work and acceleration method. Using the work and energy principle. The force and acceleration method was chapter number 17, which we did last time, and this time we are going to do the work and energy principle. So as you know that all the laws which you studied before for the case of kinetics uh, of particles, those laws are equally applicable here as well. The only thing is that previously we had particles, so it has no shape, no size, no specific volume. So the rotation factor was not there, but now here we have the rotation factor as well along with it. So we're going to study the kinetic energy, the work of a force, work of a couple moment, principle of work and energy, conservation of energy. So previously, when we talk about the kinetic energy, we used to have what? We used to have half mv square. Half mv square was the kinetic energy for the case of a particle if the particle is going through translation. This will be the same for the case of solid body if the solid body is going through translation. However, last time we do not had rotation because the particle cannot rotate. This time the particle can rotate as well. So now we will have t equals to half mv square plus half mig omega square. So instead of m you have ig, and instead of v you have omega. So now you're going to have this term as well. So this is an additional term that we are going to have, which was not there in case of the particle. Other things would remain the same. This, so we discussed like in chapter number 14 before. This is the same chapter number 18 like we had chapter number 14 before. So you can have the work of a force, work of a spring, okay. Then you have certain kind of forces which do not do any work. Now there will be one additional thing which was not there before, and that is the work of a couple. Sometimes when we have a couple moment being applied over a body, so when we were talking about a particle, so a particle cannot rotate, but now if a moment is applied over a body, the body can rotate. So the work of the couple moment, it will be considered as um will be m into theta 2 minus theta 1. M is the moment, applied torque, multiply by theta 2 by theta 1, whatever the rotation has been done. So this is going to give us the work of a moment. So this will be one additional thing which was not there before. Okay, so let's see the problem. Uh, a bar shown in the figure has a mass of 10 kg. So this is a bar. This is a bar and it has mass 10 kg. Okay. And is subjected to a couple moment of 50 Newton meter. So a couple moment. So the moment is applied here. Moment is applied here. How much it is? 50 50 Newton meter. What is the direction of the moment? Like this. Okay, so a couple moment is being applied, and a force of 80 Newton is also applied. And a force of 80 Newton is applied at this point. Okay, so this is 80 Newton applied at this point, which is always applied perpendicular to the end of the bar. So this, you see here, there is a small box here. This box represents that this force 80 Newton is always perpendicular to this bar. Okay, also the spring has an unstretched length of 0.5 meter. What is the unstretched length of a spring? Let me write here. Uh, how do I write? Okay, unstretched USL. Unstretched length. Unstretched length is how much? Point 0.5. 0.5 meter. And remains in the vertical position due to the roller guide at B. So as this bar moves, the spring remains vertical, because the position of the spring may change, but because there is a roller guide here, this is a roller guide, so it keeps the spring vertical all the time. Okay. Determine the total work done by all the forces acting on the bar when it has rotated downward from 0 degree to 90 degree. So initial condition was that the bar was at 0 degree. This is theta. See theta. And the final condition is that when the bar is at 90 degree. Okay, so we need to know that as this bar moves from 0 to 90 degree, how much is the work done, total work done, summation u. Okay, before moving over to the solution of the problem, I need to know, do you understand the problem statement or not? Is there anything within the problem statement which is not clear? Please ask. Is everything clear within the problem statement or not? Okay. Yes, Ether, you want to ask anything? And then we are not saying that the spring will not move. What we are saying is that the spring will move, but it will remain, but it will remain vertical. So have a look here. This is a situation that we have, that initially, when the rod would be horizontal, so the spring would be at this location, but vertical. And then when the rod is going to move like this, going to come, when the rod is going to become vertical, then the spring will come to this location. Okay, spring will come to this location and still remain vertical. So at any point when the spring is there, the spring would remain vertical. This is what we are saying. Is it clear? Okay, is there anyone who want to ask anything, or shall I move towards the solution? Okay, so let's move to the solution. So here we have the situation like this. So we have moment here 50 Newton meter. We have a specific force of 80 Newton being applied at this location. Okay, unstretched length is zero point 0.5 meter. Now, what are the total work done? Okay, we will have, because there is a specific force at applied P force, so we will have the work done due to this specific force or point force. Then we will have the work done because of the spring, because we have a spring here. So we'll have work done because of the spring. Then obviously this bar has a specific weight. So we will have the work done because of the weight. And now there is another thing which was not there before. That is, there is a couple moment. There is a couple moment applied over the bar. Okay, something is trying to rotate the bar. So you will have the work done because of the moment as well. So if you add up all these work dones, that will be the total work done over this bar. Before moving forward, till this step, is it clear up to everybody or not? Okay, so now let's see each and every term one by one. First of all, we have the moment. Okay, first of all, we have the moment. So the work of the moment will be m theta 2 minus theta 1. Okay, m theta 2 minus theta 1. M is provided. It was 50 Newton meter. Multiply by theta 2 minus theta now theta 1. Well, what is theta 2? What is theta 1? Now, there's one concept I want you to get that concept. Okay, for example, if it is written, let's say that theta is, let's say theta is 90 degree. Okay, let's say theta is 90 degree, and it's written, there is a function written theta sine theta. Okay, so how are we going to write it? If somebody writes it 90 sine 90, that will be wrong. We know that 90 is equals to pi by 2. So if somebody writes it as pi by 2 sine pi by 2, that will be again wrong. Okay, remember one thing: whenever theta is appearing in a function, inside a function, sine, cos, tan, cotangent, whenever theta is appearing inside a function, you need to write it in degrees. Whenever theta is appearing alone, not inside a function, then you need to write it in radians. Okay, because even when you write the theta in degrees inside a function, the end result is in radian. Okay, so this is going to be like this. So it should be pi by 2 sine 90. Okay, so this is the point here that which I want you to understand. This is the point where sometimes students do the mistake, because here, for example, when you're calculating the work done by the moment, it's moment multiplied by theta 2 minus theta 1. Now the theta 2 theta 2 is 90 degree, theta 1 is 0. So one can write here 90 minus 0, but then that will be wrong, because the theta is appearing alone here. It's not inside a function, so you do not write it in degrees, rather you need to write it in radians. So it will be pi by 2 minus 0. So it's written pi by 2 minus 0. So 50 multiplied by pi by 2 minus 0 is going to give you in joules whatever is the work done by the momentum. So far, is it clear or not? Is there anything which is not clear to anybody? Please ask. Okay, so now let's move ahead. So we have done with work of the moment. Now let's talk about work of the weight. It's the same way as before. First of all, we need to decide whether it be positive or negative. So if you look here, that the object is actually moving down, and the object is actually moving down, and there is and the weight is also acting down. Okay, so it has to be positive. Okay, so it will be mg delta h. Okay, so m is 10, g is 9.81. Okay, and delta h is, okay, here we can say that it's written like this as negative and negative, but you don't need to write negative and negative, just put positive mg delta h, like where we studied in chapter number 14. Okay, so you decide you decide the sign of the work done yourself initially, and then after that just put the formula and get the answer. Okay, then we have the work done because of the spring. So for the work done because of the spring, so what's happening? The spring is stretching, right? Initial condition of the rod was like this. Final condition of the rod is like this. So the spring is being stretched. Okay, so initially the spring was this. Now the spring is this much, because the position where the spring is connected, this is fixed. Yes, you can see in the picture again. Okay, this is the position where the spring is connected. This is the position where the spring is connected. So this position would remain fixed. So even when the bar is here, or when the bar is here. Okay, so if I draw a circle arc, so it's going to be like this. So initially this position would be here, finally this position would be here. So the spring will be stretched as the bar moves from here to here. Okay, so first of all, when the spring is being stretched, then the work done is negative. Okay, so work done is negative, so the negative sign is here, half k s2 square minus s1 square. Now what is s2 and what is s1? Unstretched length was zero point 0.5. Just remember that unstretched length was zero point 0.5. Now let's have a look at the length. Okay, so unstretched length is zero point 0.5. Suppose when the bar is at 0 degree, so what will be the length, total length of the spring? So 0.75 meter. Unstretched length is zero point 0.5. So what will be the stretch? Initial stretch will be how much? 0.75 minus zero point 0.5, it will be 0.25. And when the bar will be here, okay, then what will be the total length of the spring? Because the spring would still be at 2 meter from the pivot point. So it will be like this. So 2 meter here plus 0.75, so it will be 2.75. That will be the total length of the spring minus zero point 0.5, it will be 2.25. So S1 would be 0.25 and S2 would be 2.25. Before moving forward, is this step or is this point clear to everybody or not? Anybody has any question, you can ask. Okay, now look here. One student is asking that could you please repeat S1 and S2? Look here, when the bar is horizontal, so the spring will be here. Okay, So what is the total length of the spring at this point? 0.75. Okay, and what is the unstretched length? zero point 0.5. So S1 would be 0.75 minus zero point 0.5. It would be 0.25. Is this thing clear or not? And then S2, when the bar is going to come here down, okay, so the total, the point where the spring is connected to the bar is remain the same. So this is a 2 meter length. So this length would be 2 meter when the bar is going to come down here. So 2 meter plus 0.75. So total length of the bar will be 2.75, but zero point 0.5 is the unstretched length. So 2.75 minus zero point 0.5 will be 2.25. Okay, okay. Uh, okay, I'm going to go back to the work to the work done by the weight. But before going back to work done by the weight, since I'm here on this page, so I need to make sure that, do you understand how do we get S1 and S2? Is there any student who do not understand how do we get S1 and S2? Is 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 it clear to you how we get S1 and S2? Okay. So now let's come over to how did we get delta H. So you see, work of weight is was what, mg delta H, right? Mass is known. Okay, it's 10 kg, g is 9.81. But before that, we need to know, is it positive or negative? So first of all, since the object is moving down, so it has to be positive. Okay, has to be positive. Weight is also acting down, and the displacement is also down, so it's going to be positive. Okay, is this thing clear or not? Okay, now once we know that m is clear, mg delta h will be what? Okay, the weight of the rod will be acting at the center of the rod, right? Weight of the rod will be acting at the center of the rod. So where will be the center of the rod initially? Center of the rod initially will be at this point. Okay, and let's say, how much is the length of the rod? 2 plus 1. 2 plus 1 is 3. So the center of the rod will be at 1.5. Okay, now once the bar goes down by 90 degree, once the bar goes down by 90 degree, so now the weight of the rod is acting again at the center of the rod, and this point will be 1.5. So if you see here, from the start point to the end point, what is the actual difference in the height? Initial position for the position for the initial elevation for the weight was here. This was point 0.1, and final is point 0.2. Okay, so actually the difference in the elevation as the bar rotates from 0 degree to 90 degree will be 1.5. Is it clear? Is there anyone who for whom this delta H 1.5 is not clear? Please ask. Okay, can you open your mic?
Yes.
Okay, so let's again. Okay, you see, this initially when theta is 0, the bar is horizontal. Okay, the bar length is 3 meter. You see here, 2 plus 1 3. Okay, so the weight of the bar will be acting at the center of the bar. So center of the bar will be at 1.5 from the point of pivot point, from the point where it is pivoted. Okay, so this will be the initial point where the weight will be acting. Okay, so is this thing clear?
Yes.
Okay, now when this bar is going to rotate 90 degree, okay, so just imagine how this point is going to move. This point is going to move in a circular path as well, okay, where the weight is acting. And when it has moved 90 degree, so how much elevation this point has dropped, because it moved in a circular path, in a circular fashion. So from 0 to 90 degree, how much elevation drop has done? That elevation drop is delta h, so it will be again 1.5, because it's a circular path. Is it clear?
Okay. Yes.
Okay, thank you. Anyone else who think who do not understand how did we get delta h as 1.5? Okay. So we have work of the moment, work of the weight, work of the spring, all done. Okay. Now what left is the work of the point force. Now work of the point force. How do we find work of the point force? Okay, so let's come here. So look, our initial condition of the bar was here. Final condition of the bar is here. The point force was acting initially at this point here. Finally, it is acting at this point here. Okay, and since this point force is constant, it is not changing. So we need to see that what distance it has covered. So it has covered a distance equals to this distance of the curve. So this distance is s is equals to r theta. We know the radius, and we know the theta. The theta will be 90 degree. So s is equals to r theta is actually the distance which is covered, which has been moved by this force applied as a constant force, which is 80 Newton. Okay, so considering that, let's come here. So work of the point force is the force multiplied by the distance. The force was 20 Newton. Okay, multiply by, sorry, 80 Newton, multiply by the distance. Distance is r theta, where r will be the radius 3 meter, and theta is will be pi by 2. Okay, why? Because theta is not coming in a function, so I'm going to write here pi by 2. So it's going to give me that how much is the work done by the point force. Is this point clear or not? Is there anyone to whom this point is not clear? Please ask. So now once we have all the work done, what we are going to do is just we are going to add them up all together. So add UM with UW plus US plus UP, all of them together, and you're gonna end up with whatever the net work done. Okay. So that was the first part of the question. That was basically the first question. Anybody want to ask anything, you can ask. Okay, just wait a little so that the azan finishes, and then we're gonna continue. Okay, so now let's move over to the principle of work and energy. Okay, the principle of work and energy is very similar to what you have been doing before, and that was basically T1 plus summation U1 to 2 equals to T2. But the only difference is going to occur is in the T1 and summation is in the kinetic energy and the summation of work, because now the rotation factor is there. So in the summation of all the work done, so previously um, or the work done by the couple moment, was not there, but now this time maybe if the couple moment is there, then you will have um as well, which is the summation of, which will be in the summation of all the work done. So work done by the couple moment, and that will be um is equals to m theta 2 minus theta 1. The second thing is in the kinetic energies. In the kinetic energies, initial or final, previously we just used to have half mv square, but now we can have kinetic energy due to translation, or we can also have kinetic energy due to rotation. So if a body is not moving from one place to another but rotating on its own axis, then the body is going through, or there is a specific kinetic energy of the body based upon the velocity, the angular velocity of the body. So the kinetic energy will have two components, one linear component, one angular component. Half mv square, which will be the linear component, and half, instead of m, I'll have I, and instead of v, I'll have omega. So half I omega square will be the angular component. So you'll have linear and angular component for the case of the solid bodies. That's the only difference. Other things would remain exactly the same as we have been doing before. So you see here, we have previously we just used to have half mv square. Now we'll have half I omega square as well. And previously we used to have work due to the point force, work due to weight, work due to spring force. But now we might also have work due to couple moment. So that's the difference only. So okay, so let's have a problem statement. The 30 kg disc shown in the figure is pin supported at its center. So this disc, which is 30 kg, and it is pin supported at its center. Determine the number of revolutions it must make to attain an angular velocity of 20 radian per second starting from rest. So it's going to start from rest, but we need to see that how many rotations, how many revolutions it should make so that its angular velocity become 20 radian per second. It is acted upon by a constant force of 10 Newton. So 10 Newton is the force which is being applied here to a cord wrapped around its periphery, and a constant couple moment of 5 Newton meter. So there is also a couple moment applied. So something is trying to. So now there are two things which are trying to rotate this disc. One, because of the unwrapping of the cord, because of the application of this force. So when this force is applied, so it's going to unwrap this cord, and because of that, this disk is going to move. But other than that, there is also a specific moment. Something is trying to rotate it from the center. Okay, and that is, there is a couple moment here, 5 Newton meter, which is acting in the same direction as that of the rotation caused due to the cord. Neglect the mass of the cord in the calculation. Okay, so before moving towards the solution of the problem, first of all, do you understand the problem statement or not? Before moving towards the solution, I didn't understand the shape. Uh, which shape? This is a disk, and there is a cord. So like
Uh, what is this thing in the middle?
in the middle, we have something which is keeping the disk at that position. So it's a support, pin support. So the disk is being supported from the center. So the disk can only rotate.
Okay.
Okay. So before moving towards the solution of the problem, do you understand the problem statement? Everybody, is there anyone who do not understand the problem statement? Please ask. Okay, now let's move over to the solution. Okay, so we have this situation. We have T1 plus summation of all the work done from 1 to 2 equals to T2. Okay, so first thing is that T1, and since we have the body being rotating and there is no translatory motion of the disk, so linear motion will be zero. So there will be no linear velocity. So half mv1 square will be zero. Okay. Secondly, we do not have any because the disk is not moving, so there will be no work of the weight. There is no spring here. Okay, there is a couple moment applied. Okay, and half mv2 square will also be zero because there is no final motion of final velocity, linear velocity of the disk. And we are starting from the disk is starting from rest. Since it is starting from rest, so omega 1 will also be zero. So we're going to end up with this equation. Before moving forward, is it clear or not? Okay, so now we have this equation. Now in this equation, let's see each and every term one by one. The force is fixed, it's 10 Newton. Okay, how much is has the has how much distance has been moved by the disk? Okay, so it will be S is equals to R theta. R will be the radius of the disk. Theta we don't know. This is what we need to know, that how many number of revolutions has been made. Okay, then we have M, moment applied, equals to, let's say it is started from theta 0. Then what is the final theta, we don't know. Okay, so this is again unknown. Theta equals to half into I naught. Now I naught we need to provide you, for the case of a disk, what will be the moment of inertia if it is being rotated from the center. So it will be half mv half into mass into radius square. So this will be the formula provided to you in the exam. Okay, multiply by omega 2, that what will be the final angular velocity. We want it to be 20 radian per second. So if you substitute all the values, you're going to come up with the answer that theta is or should be equal to 17.142 radians. Then we can just divide by 2 pi to convert it into a number of revolutions. So it should be 2.728 revolution. So starting from rest, after 2.728 revolutions, this disk will have a velocity of or angular velocity of 20 radian per second. So we have solved this problem. Is there anything within the solution of the problem which is not understood by anybody? Please ask. Is the solution clear? There is an alternate solution to this problem as well. This is according to the methodology of chapter number 17. So, anyways, you can go through with this methodology as well. As I told you, this chapter number 17, 18, there are different techniques of solving the problem or solving the kinetics of the problem. So, all the techniques are equally applicable and they are equally correct if you apply them correctly. So, you can see here the same problem was solved using the technique of this chapter here, and then later on in the next slide the same example is being solved using the technique of chapter number 17. So go through it yourself if you want to. Let's have another problem. The 50 kg pendulum of the Charpy impact machine is released from rest when theta is 0. The radius of the gyration is 1.75 meter. Find the angular velocity of the pendulum when theta is 90 degree. So again, it's a similar kind of a problem, the one which we were solving before, but in this case now it is a Charpy impact machine, and theta is again from 0 to 90 degree. But here one thing is given: we are given the radius of gyration. Now, why we are given the radius of gyration? We are given the radius of gyration because this is a Charpy impact machine, so it's a very irregular shape. You cannot find I naught for this shape. You cannot find I naught for this shape. So what is given is that since this object is rotating at point A, so here we need IA. So for IA, we are actually provided with KA, radius of gyration, because I told you if you have KA, you can find IA. Okay, so this is the technique that we are going to use in this question. Let's see the solution. Release from rest, theta is 0 to theta 90 degree. We need to find what is the angular velocity. Okay, again, we can apply the principle of work and energy. In this principle of work and energy, first of all, there is no point force. First of all, there is no point force, there is no spring, there is no couple moment. The only thing which is causing it to move down is the weight. Okay, then the second thing is that this thing is moving in a rotatory motion. Okay, so there is no linear component. Okay, so we can just ignore the linear component here. Okay, so what we are left with is the angular component for the kinetic energy, half Ia omega 1 square plus W delta y equals to half Ia omega 2 square. This is what we have. Now omega 2 we already have. Ia we can find because we know what is the relationship between I and radius of gyration. So Ia is equals to mka square. Since we know what is Ka, we know what is the mass, so we can find what is Ia. Okay, we know what is the weight. Okay, we can also find what is delta y, the same way like we did for the case of last to last question when we had a bar which moved from 0 to 90 degree. The same way we're going to find delta y here as well. Omega 1 will be 0 since it is released from rest. So following all these steps, we're going to get what is omega 2. And actually at this point, this question is also solved. If you want to ask anything, anybody want to ask anything, please ask. Is the solution clear? Okay. So now this is the conservation of mechanical energy or the conservation of potential energy. But anyways, we can solve the problem using the principle of work and energy as well in the same way. So let's have this problem. The 30 kg rod is released from rest when theta is 0. The spring is unstretched when theta is 0. So this spring is unstretched when theta is 0. Find the angular velocity of the rod when theta is 30 degree. Okay, so you see here this is 1.5 meter, this is total 2 meter center to center distance. So when theta is 0, so the unstretched length of the spring will be how much? 2 minus 1.5, that will be zero point 0.5 meter. That will be unstretched length. Now let's see the solution for this problem. Again, m is 30 degree released when theta is 0, and find out the omega when theta is 30 degree. So we can use this same methodology here. Now in this case, this time again we have no linear velocity. Okay, so the linear components are not there, and since it's starting from rest, so angular velocity initially is also 0, and then there is no point force here. There is weight acting, and there is a spring, and there is no couple moment. So we're going to end up with this form of the equation. Okay, then once we have these things, so we know that weight is 30 kg into 9.81 uh, into delta y will be delta h. So delta h will be how much? It will be half k s2 square minus s1 square. S1 will be 0 because at theta 0 degree it was unstretched, so it will be zero point 0.5 minus 0.50. And then we need to find that what is S2. So S2 will be now this is a right angle now this is a triangle actually. Okay, so here theta is 30 degree, this is 1.5 meter, this is 2 meter totally. So we can find this length. Now it's up to you that how do you find this length. There are multiple ways of finding it. What I did was that I made two right angle triangles, and since I know this length, okay, and I know this angle, so I find what is this length and what is this length. So now I know what is this length, and then using this length and this length I find out what is this length. So there, so this is like 2 or 3 step procedure where how you can find this length. Or if you want, you can use directly the cosine law, because you have two length and an angle in between them. So you can use the cosine law to actually find out this length. Okay, so it's up to you. It's up to you which mathematical method you want to use. It's up to you. So anyways, we find what is S2, then minus unstretched length is going to give us that what is the actual amount of S2. And that's it. Now we have to use I naught. Okay, so in this problem, we would be given that what is the formula for the I naught. But the I naught formula will be for if the rotation was from the center. Since the rotation is not from the center, rather the rotation is from one of the corner, so we need to use then parallel axis theorem over I naught to find out what is so what is the actual I. So this is the I naught, this is the IG, sorry, this is the IG, and then this whole thing is the parallel axis theorem, where we use IG and the perpendicular distance between the two axes of rotations to find out what will be I naught. So anyways, in this case, we're going to end up with getting omega 2. Within the solution, if there anything which is not clear, please ask. So here the solution is done here as well. After that, you have another problem. So with this, our chapter number 18 is finished. We've gone through all the problems in this chapter. Whatever the problem that I have not gone through it, you can go through it yourself. But the idea is the same as of chapter number 14. Only the thing is that few components were added into it because of the rotation factor being added due to the solid bodies. So if there is anything anybody want to ask, you can ask. Actually, with the finish of chapter number 18, we are actually done with the syllabus, with the whole syllabus of dynamics. Chapter number 19, I don't think that the other sections might be able to do it. And so since they won't be able to do it, so we will also not do it. So here our this is the 12th week, and in this week actually we are actually done with our course for the dynamics. So anybody want to ask anything, you can ask. Your next exam will be from chapter number, your first exam was from chapter number 12 and 13, and your next exam will be from chapter number 14 and 15. So it will be from two chapters. We have already discussed with Dr. Salim. Inshallah, a student is saying, Doctor, please, we want after the mid and final, we want to feel happy. I hope that you will feel happy after that. Inshallah, but you need to work. Okay, please try to work over the problems, classwork problems, homework problems, practice problems, as much as you can. The more you practice, the better for you. Okay. Uh, if you have a question, please ask. Uh, Student is asking, will you change the scale of the exam? Well, let's wait till the second exam. How can we use dynamic as a biomedical engineer? Okay, a student is asking that how can we use dynamic as a biomedical engineer? Look, this course itself is like a knife. Okay, so if you go to a store and you want to purchase a knife, okay, and you want to ask, okay, how can I use knife? It's up to you. You can use knife in your kitchen. You can use knife in your bedroom. Use knife in your drawing room. You can use knife outside. It's a tool. You can use the tool the way you want. Okay, so dynamics can have tons of applications in different aspects of biomedical engineering. Now I myself am not does not belong to the biomedical engineering field, so I do not know much applications, but those who are in this field can actually explain you that what is the reason why this course has been placed in your degree plan. So there's definitely a reason, and there's definitely uses of this course in your field. So it's right now what you are learning is a tool. Okay, so how to use it, now it's up to you where to use it and how to use it. My student is asking, will you change the scale of the exam? Let's wait till the second mid and then we will see. So anybody want to ask anything, please ask. uh, okay, is it possible for you to give us revision questions? I don't know what kind of revision questions you're asking. Where can we find The Rix, don't know. The second mid will be out of 25. Uh, Second mid, yes, it will be out of 25. That has similar ideas to the exam. Something extra we can practice. Something extra we can practice that has similar ideas to the exam. Actually, the book is with you, so the exam will have the similar idea as that of the book. But if you want really to give you exactly the same thing as is there in the exam, so you will have it only in the exam. Doctor, what will we do? Review before the exam? Sure, we can review before the exam. But when we will be reviewing, I would like to know that what is the thing that you want to review? What are the things that you feel? Where do you feel the difficulty? So the first thing would be better that you try yourself to work, and then after that, once you know that okay, this is the point that you need to discuss with me, so we can have a review. How many questions will be in the mid two? Right now, we have not yet made the second mid. So, anyways, I don't know right now. So, it will be 1 hour for sure. But for 1 hour, if there are lengthy questions, then the questions will be less. If there's short questions, then the questions will be more. Can we have the lectures record? Okay, I'll provide you the lecture record, no problem. I don't have the lecture record from the early lectures, but from for the later lectures, yes, I do have. So I'll provide that. So anybody else who want to ask anything? Doctor, if I want to get good mark, like almost full mark, what should I prepare for quiz? Okay, then you should prepare both chapters very well, chapter number 14 and 15, and inshallah you'll get full marks. Okay, any other question anybody else want to ask? Is it possible to give us more than 1 hour? Look, for the exam, the problem is that normally the exam is scheduled earlier, and I mean the place where you will be giving the exam, maybe someone else have an exam just after your exam. So we really don't know whether we can give more time or not. First thing. The second thing is that we will not be personally invigilating your exam. So there are other invigilators. So we cannot really force the invigilators to spend more time uh, for invigilation. So there are some constraints. We can give more time, a little more time, but because of the constraints, I would say that it will be difficult. So try to complete the exam within 1 hour. I feel like the time is short, so we panic and don't do well. No, inshallah. If you practice well, then you will not feel panic at all, inshallah. So, anyone else want to ask anything? Okay, for that's it for today and this semester. Uh, Thanks a lot and best of luck for your exams.
Doctor,
Yes,
can you answer one more question in the chat?
sure. Which one? Just a minute. The required homework for chapter number 14 and 15 only. Yes, the required homework for chapter number 14 and 15 only. And no, you have 16 and 17 as well. Okay. Uh, okay, 14 and 15 only right now. But when you come for the final exam, then you bring yourself the homework for chapter number 16 and 17. I'm going to put the marks for the homework 16 and 17 before, but I will deduct the mark if I do not get the homework uh, during the final exam. Can we do it for ourselves only? Yeah, sure, you can do it for yourselves only, but I need to take a copy of it, you know. Okay, so not, not can we do it for ourselves only, not handle it? I'm sorry, I couldn't understand what you want to say. One student initially said that can I answer one more question, but I don't know, she didn't ask the question.
Doctor,
Yes.
in the final exam, is it possible to put more question like a bonus?
Bonus. I'm hearing about it for the first time. What is this question?
If the grade is low, the doctors put one more question in the final exam. So the students who get the mark in it get a bonus grade.
Uh-huh. And if the student get full marks in the final and also the bonus, then
Yeah, the bonus يعني it's the sum all the grades, not for the final exam only. So it's added to the quizzes.
oh, and if the student is already a 60 out of 60 and he got 40 out of 40, and so then
Nothing will happen. It's just the bonus.
anyways, this is first time I'm hearing about this thing. I've been teaching this course for the last 2 years, no, 3 years actually. And Dr. Salim is senior than me, and he has been teaching this course even 2 3 years before than me. So I will discuss it with him and see what he says. But I don't think, since we have never practiced this thing here in this course, so there's very little chance that this thing will be allowed. But let's see. We're going to discuss in the committee, and we'll see.
Doctor,
Yes.
can you come, I mean, at the day of the mid, can you come to the college if we have some questions or?
I can come, but I think it is. I mean, they don't allow, or last time when I come, they directly just say, okay, give us the papers and we're gonna take care of it. So for me, no problem. But the only thing is that I don't want to go against the university regulations.
No, it's okay. We have a mid before with a male doctor, and he come to the class, and we ask him.
Okay, I can come, no problem.
Okay, thank you.
So we can apply this in 2 courses. Okay, if your department apply this thing in 2 courses, anyways, we're gonna discuss and we're gonna see. If possible, we're gonna do it. But since we have never done this before in any of our course, or have never heard about it before as well, so I don't know. Let's see. Project using ANSYS. Um, Again, as you said, that Dr. Salim said that it's if it's good, he will count it as a homework. It's okay, but only within the part of the homework we can count. Nothing, nowhere else. Okay, so regarding the exams, whether you take it a major exam or you take it uh, the final exam, so it has to be whatever the exam marks you get. Okay, So if you do any additional project, okay, so maybe if you're getting less mark in the homework, so maybe it can compensate for that. But I think majority of you will be getting like almost full marks in the in the homework. So it's just a useless activity. I mean, it's not going to give you any benefit. No, the grades cannot be passed to other friends. So I know it was a bit. Okay, yeah, as an experience, of course, a good experience, sure. Okay, I think that's it for today, and best of luck for your exams, and best of luck for your future. Thank you.